Alrighty then, so today I'll be talking about binary trees and recursion in general. I'll start with a bit of a conceptual demo and then we'll go into some code so you can open up your IDE and get ready in case you want to follow along. So in terms of the conceptual demo, so what we're thinking about here is we're thinking about binary trees, and the way binary trees work is you have a value, a node, right? And that node has a value. And then that node has two children nodes, which will be the left. Wow, that was left and the right nodes. And so for a normal binary tree, these can be any value, so 2 could be on the left, 3 could be on the right, whatever, it doesn't matter. But for a binary search tree in particular, the left value must always be, so we'll call them children and parents actually, so this would be the parent in this case, and then these would be its children, and then in the case that these are the parents, these would be their children. So this one's children would be this, and then this one's children would be this and this. So it's important. So these will not be referred to as the children of this node. So that's just an important thing to remember. But anyways, so when we have a binary search tree, what has to happen is that the node on the left has to be smaller than the node on the right. So you could have, you could have -3 here, and then, maybe nothing can go here because we have 1 and 0. It really depends on how you set up your rules. You could possibly have a 1 here, depending on how you set it up. But you could also maybe have nothing here, maybe 0 goes here. If you have a duplicate 0, or maybe just nothing's going to end up going here, in which case you just wouldn't have this node. This would point to a null reference. So on this side here, maybe this would be null, and then this would be 3, but let's look at an example where we can have 2 children. So let's say that this is -5, then -7 can go to the left of it, and -3 can go to the right of it, right? Because -3 is greater than -5. So what happens here is when we're inserting -3, we go, okay, so is -3 less than or greater than 1? We go, okay, -3 is definitely less than 1, so we'll go to the left, and then we go, okay, -3 is greater than -5, so let's go to the right. Now, if we look at -7, with -7, we do something similar where we go, okay, is that less than or greater than 1? Okay, it's less than 1. Okay, is that less than or greater than -5? Okay, it's less than -5, so we go to the left. So we just keep going down a step, and every time we ask, is it less than or is it greater than? If it's greater than, we go to the right. If it's less than, you go to the left. And so that's how a binary search tree works. A normal binary tree, we can just have any values anywhere, but the important thing is that every node can have a maximum of 2 children. It can have no children, so maybe both are null. That's fine. It can have 1 children, maybe 1 is null. And it doesn't matter which one, so it could be the other side could be null. That's not important. But it can't have 3 children. That's not an option. And it can be of any depth for a binary tree. There's something called a height balance tree, where the tree restructures itself in a particular way that makes sure that it doesn't get too long on one side and then too short on the other, because what happens there is that maybe some of our functions take a longer time to run because we are spending all this time going through this really long chain, when if we'd split it up throughout the tree, we could just go bop, 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 and we'd be done. So now let's also take a think about recursion. So let's think about how with recursion we could solve something simple like writing the Fibonacci sequence. If you don't know what the Fibonacci sequence is it's a sequence that looks kind of like this. And if you don't see what's happening here, all that's happening is that we're taking, so we start with a 0 and a 1, really, and that's just how we have to start. But then we add the previous two, and 0 plus 1 is 1. Okay, then we add these two. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 3 is 8. And then 5 plus 8 is 13. So that's the Fibonacci sequence. That's how you move up. And let's say you wanted to find the next number, it'd just be 21, 34, etc., etc., etc. You can just keep moving as far as you want. So when we think about this, we think about this kind of iteratively, right? So we start at the left, and we move to the right? Because we're writing out the whole sequence. So we're going 0, 1, 1, 2, and then 3, and then 5. But what if I just say, hey, I want the 8th term? Okay? So one way of thinking about that is you can say, hey, okay, let me build up to the 8th term. So that would be 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the 8th term, right? And you would go through iteratively and you'd write that all out. And the other way of thinking about it is, okay, so the 8th term is the sum of the 7th and the 6th terms. What's the 7th term? The 7th term is the sum of the 6th and the 5th terms. What's the 6th term? The 6th term is the sum of the 5th and the 4th terms. And then the 4th term is the sum of the 3rd and the 2nd, etc., etc., etc. So we have this, kind of big list of things that there is a sum of. But that would be an example of a more recursive way of thought. And maybe the Fibonacci sequence is faster iteratively, but it might be more intuitive recursively in some ways, because you're saying, okay, I have the 8th term, and I know that's the sum of the 7th and the 6th, so let me figure out what those are. Oh, how do I figure out what the 7th term is? That's the sum of the 6th and the 5th, right? So when we're thinking about recursion, we're really thinking about something that can be broken down into steps that build. So that's not necessarily the way something would work iteratively, right? Let's say I wanted to just add 1 to every element in a list iteratively. That would be like 1, 2, 3, 4. And I wanted to add 1 to everything, so I'd go, okay, so the first one, 2, then the second one, 3, then the 4, and then 5, right? And maybe that would be an example of a problem that we don't want to solve recursively, because we're not building something that we're referring to previously, right? So this 5 is not dependent on what this 4 was. That doesn't matter. So we don't want to think about that in a recursive way. What we want to think about in recursive ways is things that build up. So an example of that might be, let's think. So a good example of that might be, well, the Fibonacci sequence is definitely a good one. If you've heard of the Towers of Hanoi, that's a problem where you have these rings on these towers, and this is a really good problem to look up if you're completely unfamiliar with it. So you have 3 towers and some rings, and your goal is to get this stack of rings over to this side, but the catch is that a small ring can never be underneath a larger ring. So we have to figure out, okay, so this ring can go here first, so then we have the small ring, and then this ring goes here, and then we have the big ring. Maybe we move this ring back here, and then we put this ring here, and then we put this ring here, and then this ring here, and then this ring back on top. And that might be really hard to follow along with. So you would have, let me break it down so it's a little bit more clear. But that would be, that would be one way of solving it, is maybe thinking about it like that. And then there's a recursive solution to the problem too that I won't go into because it's a little bit, I guess, a little bit long for this, but I would definitely look that up if you're struggling with recursion. That can be a really good problem to kind of get you more comfortable with recursion. But and then so I would look that up, and then I just blanked out for a second there. Okay, so other than that, what are other things that can be done with recursion? Binary trees are a great example of something that's solved primarily with recursion. Let's think about something closely related to a binary tree. It's called a binary search. So binary searches is when I have a list of numbers. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8. And binary searches and binary search trees are actually very similar. But when I'm doing a binary search, I go, okay, I want to find the number 2. So I'm going to find the number 2. First, I'm going to check right in the middle. Hi, Kristen. So you're going to check in the middle, and you're going to say, hey, is this less than or is this greater than 4? So 2 is less than 4. So now we're going to repeat the same action, but with this left side. And now I go, okay, hey, is this less than or is this greater than, let's say 1. Let's say we round to the left. So it's greater than 1. So now let's go over here, and now we're checking here, and now is it less than or is it greater than 2? It's actually equal to 2. Okay, so this is our position here, so that's position 2, right? So that would be an example of a binary search, which is very similar to a binary search tree in a way, and this is another great use for recursion. So those are some of the uses for recursion. Now let's actually apply some of it with some actual code here. So let's go ahead and start coding a binary tree in general, and then we'll see if we can make it more of a binary search tree. So when we have a tree, the first thing we need is the root node. So that's going to be like the top node, right? The very top node is called our root, or our head node. I'll call it a root node, but you'll see the word head a lot too for it. And so now we need to define what a node actually is, because that's not something that Java just gives us like that. So let's say what a node is. So let's have it be a private static class, because we don't need the node to see anything in tree, and we want node to only be used in tree. So our node is going to have a left node, right? It's going to have a right node, and it's going to have a value. So you can have that value be any data type. I'm going to go with an integer because integers are pretty easy to work with. You could even do generics though if you wanted to for this. And so when we construct a node, we need to give it a value, and then its left node is going to be null off the bat, and its right node is also going to be null off the bat, but its value is going to be that value that you passed in. So the other thing is that we're leaving these public because they can only be accessed by the tree class anyways. And we never want to expose node to the outside world. So we're never sending a node outside of the tree class. We're keeping the node within that one tree instance. The only thing that the user or the client code would see would be the values. The client code doesn't know that node even exists because, again, node is a private class. So let's think about a method that we might want to add here. So one thing that we might want to do first is actually let's make a really basic tree. So let's say, sorry, not public. let's say my tree is equal to a new tree, and then I want to give that tree a root. So let's see, so we'll say tree.root is equal to a new node of 5, and then maybe we'll say that tree.root.left. So what I'm saying is, okay, here's what I'm saying here, is I'm saying, okay, I have my tree starts with a node of 5, and now I want to look at this left node. Let's fill that in. So I'm saying that that's going to be equal to a new node with a value of 8. So let's put that 8 there, and we can get rid of this other stuff now. Oopsies, I meant to move that, not delete that. Okay, so we have our tree with our node with a value of 8, and then let's add a couple more nodes in. We'll say let's add a couple more nodes in here, one on the right side maybe, and then maybe another one there. And so this this tree is going to end up looking something like, let's make this value a little bit different so we don't have 2 8s. But let's say, okay, so the left node of the root is a 9 now. Oops. So that's a 9, and then we see what's the right node of the root. So the right node of the root is an 8. What happens next? We say the left node's left node is a 2. So we go, okay, so left node, and then the left node of this node is a 2. And then we say, okay, the left node's right node is a 7. So we go the left node, and then the right node is a 7. And then what is this 8 left and right pointing to here? These are just nulls, right? So there's no node here. It's just a null. So let's see what happens when we run this. Let's put something here so that we can put a breakpoint, and let's run this. Oops, that's the wrong thing. Let's run this, and let's run it in debugger mode. Okay, so we have our tree root, and our tree root has a left node with a value of 9, right node with a value of 8, and the left node has a 2 and a 7 child. So that's exactly what we wanted to see, right? We have our tree, and it looks exactly like it does here. So that's perfect. So from here, let's add some methods to do some of this work for us, because we don't want a client to be going through and being like, let me manually add this node to the left side here and then the right side here. That's a lot of work for the client. So let's add an insert method, and we're gonna make this a binary search tree. So we have some rules for where to insert, and we're not just inserting randomly. So we want to insert by value. We want to insert a value in, right? Because again, remember, client code doesn't have access to a node, so they're not giving you a node to insert in, they're giving you a value to insert in. So then we're going to say our root is equal to our insert root value. So what's happening here? This is called, well, for one, what's happening here is we're going to be using method overloading to have this method be exposed to the public, and then another method with a method signature of private node insert node root int val, and this is going to be our private method here, and this is what's going to do the brunt of the work, and this method is just for public use because the public can't pass in a node, right? So we need to be keeping track of what node we're on when we're going through something, when we're going through a tree recursively. Because remember, when we go through a tree recursively adding something, we go, hey, let's look at this node. Is it less than or is it greater than? If it's less than, let me add to the left. If it's greater than, let me add to the right. Okay, now let me look at that left node. Is it less than or is it greater than? If it's less than, let me add to the left. If it's greater than, let me add to the right. Okay, so what's happening here is we're going to say root is equal to insert root val, and you don't necessarily have to do it like this. There's definitely ways to get around using this equals operator. You could also just have it be insert, but then you'd have to code it out in a little bit of a maybe less intuitive way. But this way, what we're having here is that this is going to return the root node. So let's say, well, for one, let's return the root, because we want to do that at the end every single time. But now we need to make our changes to our root node. So our first change might be, well, our first check is going to be, hey, is our root null, right? So if root is equal to null, then we're going to say root is equal to new node of val. And that's all we're going to do there, right? We're going to say, hey, if we don't have a root node, or if the node we're on right now is empty, let's put a node there of val. And now this kind of has a double use, right? So this is going to be is if the very first node isn't there. So if this tree was just made and there's no root node yet, we're just going to throw this node there, right? We don't have to do any other checks or anything. But what also happens is this will also run in the case that, hey, let's say, okay, so the root node doesn't have a left child, and we discover that the node that we're trying to add is to the left of the root node. So we're just going to say, hey, let's stick it on the left, because the left is null in that case, right? And then so the left becomes the new root. Then we're going to say left is equal to null. Hey, that's true. Okay, so the left is equal to this node. And then we can return this node back up. And we'll see how this works in a second, why returning it up like this will keep the structure of the tree. So the next thing we can do is say, okay, so we've established that the root isn't null, which means it has to have a value, because our node is constructed with value, right? So our node has a value. So let's say our value is less than our root, whatever node we're on right now's value. You know what? I'm gonna name this current instead, because it's not really the root of the whole tree every time, right? It's really just the node that we're looking at that time. So it changes. So our current would first be, you know, the root node, and then maybe it'd be the left child of the root node, and then the left child of that, and then the right child of that. So current changes, you know, every time this function is called, it's going to have a different node there. So let's say, okay, so if the value is less, then we want to go to the left, right? So we'll say current left is equal to, so now you might be tempted to say, okay, new node, value, okay, we'll call that good. So why would this be an issue? This would basically mean that we would never move another step, right? We would just immediately say, okay, it's less than, so let's replace the left node. But what if there's already a node there? So we can't do it like that. Instead, what we do is we're going to call this insert function again, and this is where the recursion comes in. So we're going to say insert on the left node, and we're going to try this again. So we're going to say, okay, now let's try again. We're going to try and inserting on the left node, and if the left node is null, it'll just replace that node, right? And we're good to go. And it'll return that node up, and then this node's left node will be equal to that node that gets returned up. And that's where this change x thing works. X equals change x concept comes in. That's what we're doing here, is saying current.left is equal to a changed left, and that should actually be a current, not a root. So we're saying current.left is equal to a changed current.left. So we're going to want to do the same thing for the right side. Right is equal to insert right val. So this works the exact same way, except it goes on the right side, and then when all is said and done, it returns the node back out. So if this is not making a whole lot of sense to you, I really encourage you to set a breakpoint, use the debugger, see what's happening line by line with every recursive call. Follow along, maybe with a pencil and paper, maybe set watchers on the variables here. Really just go line by line through what's happening. And I think that'll really help you get a little bit of a better understanding of recursion in general, as well as how binary trees work. The one thing here is that when the value is equal to current.val, what are we doing? We're actually just returning it. So in this case, this tree, it's not adding a duplicate value, right? So if I was to go up to this tree and I was to say, hey, sorry, so this isn't even a binary search tree actually. This is just a binary tree, but if we want to make it a binary search tree, it's not too bad. We could go like 3 and then 4 here. Okay, so now if I go through and I say 3, I want to add 3. Okay, so I go check. Hey, that's less than that, so let's go this way. Hey, that's the same as that, so what am I going to do here? I'm just going to do nothing. I'm just going to say, hey, it's already in the tree. Can ignore it. It's fine. So in some cases, maybe you want to handle something in particular when you have duplicate values entering. So maybe you'd write an extra else clause, val is equal to current.val. Maybe you do something there. Sorry, that would be an else if. Or I guess you could just write an else and not have a thing there. But, you can decide on your own. Some people like to do a greater than or equal to, less than or equal to on one side. It's all just a choice thing. So now we have this tree here, and we know that this doesn't make a binary search tree, right? This makes a binary tree. So let's rewrite this, but with insert statements instead. So that'll look something like this. And so all I did there was I said tree.insert 5, tree.insert 9, tree.insert 8, tree.insert 2, tree.insert 7. It's pretty straightforward. It's just calling this insert function on every single one of these values, and let's see what happens here, what our tree structure ends up looking like. Oops, we just hit that breakpoint, and we need to run with the debugger. So we go tree, okay, so tree, okay, so the 5 is at the top. That makes sense because we add the 5 here, and it immediately gets put as the root node. Then its left side is going to be a 2. Okay, that makes sense. 2 is the only thing that's less than that, and the 2 doesn't have any children. So let's look at the right side. Okay, so the right side is going to be a 9. That makes sense. The 9 is added next, and it's bigger than a 5, so it goes to the right. Okay, and then what's on the right side of the 9? Okay, there's nothing there. That makes sense because 9 is the biggest value in the tree. So let's take a look at the left. The left is the 8. And that makes sense because 8 is greater than 5 but less than 9. And then let's look at the left again, and we have a 7, and that makes sense also because 8 is it's greater than 5, it's less than 9, and it's less than 8, so it would go to the right and then to the left and then to the left. And that's where it is. So that's one way to actually check if your code is working. You can just go through the debugger and be like, hey, are all my values in the right place? This is just really a good way to do it. It's also a good way to really figure out what your code is doing, because sometimes I feel like with recursion it's really easy to write code and then you kind of just space out for a second and you forget what's really happening there, because recursion's hard. It is. So that's an example of how you can write an insert function. And really quickly, I'm going to show you a more general example of recursion that's not related to a binary search tree or a binary tree at all. So I want to show you how you could write the Fibonacci sequence in code. So I'll also show you possibly something new which is the switch statement in Java. You might not be familiar with it. You might be familiar with it. It's pretty cool. I like it. And so the way the switch statement works is you say, I want to switch on n. And you remember what I said about the Fibonacci sequence is what we're doing is, let's say I want the 8th number in the sequence. I'm going to be looking at the 7th and the 6th, and then I have to be like, okay, how do I define the 7th? I need to look at the 6th and the 5th, and so on and so on. So n here is what term in the sequence it is. So it'd be the nth term in the sequence. So for example, the sequence is 0, 1, 1, 2. So 2 would be the 4th term in the sequence. So we know that the first term in the sequence is going to be a 0, right? We know that for a fact. So we go case 1, return 0, right? Then let's say case 2. So what's happening here? Case 2, return 1. Right? Because the second term is always going to be a 1, and that's just kind of how we've defined the Fibonacci sequence working. Is the first term is a 0, and the second term is a 1, and then from there, everything else is dependent on the other things. So we're going to say default, which is kind of similar just to the else. So if you think about this in if and else's, this would be like, okay, if n is equal to 1, return 0. Else if n is equal to 2, return 1. Else, let's do this. So what are we doing otherwise? We're returning Fibonacci of the 1 term before plus 2 terms before. And then that's actually it, I think. That should just work. So if I print it out, let's comment this out. And if I print it out and I say, okay, I want the 4th term. The 4th term, do we remember what that is? I think that was a 2, right? So, yep, exactly, perfect. Let's quickly check what a higher term might be. Fibonacci sequence, let's see. Looks like the 14th term is 377, so let's see what that is, if our thing is working. Oops, sorry, that would be the 14th term if you start at 0, at the 0th term. So, yeah, so the 14th term, assuming that, that this was 0 and this was 1, would be 377, but since we did it this way, where we say that the first term in the sequence is 0 and the second term in the sequence is 1, some people define it as the 0th term in this sequence is 0 and the first term in the sequence is 1 and the second term is 1 also, etc., etc. But if we do it this way, that is correct, because if we say that the first term is 0, then the second term is 1, so on and so forth, we'd get the 7th term is 8, the 10th term is 34, and the 14th term is 233. And we can test any of those. So we can say, okay, so the 7th term should be 8, and that's in fact what we get. So that's pretty much another use of recursion. And again, if you don't understand what's happening, you put a break statement, you put a little break thingy here, you just click outside the margin. If you're using IntelliJ, a lot of IDEs have some form of this, and if you're not using an IDE with a debugger, you might want to look into an IDE with a debugger, because IDEs with debuggers are great. Debuggers are great. They're just very useful. Strongly recommend them. So that's pretty much an introduction to recursion and binary trees. Thank you for watching.